everything I'm talking about is joint work with Tony Yu, who's here. I see him on the screen. So this is all with Tony. So this is with Tony Yu and Paul Hacking. And everything that we're doing, this is really under the auspices of the GrowZebra program. All this stuff is you know, just all the way through infused with stuff from joint work with Mark and Bernd. Not this particular project, but you know, lots of stuff. So let me start with something just that is not about mirror symmetry or anything. It's just a cool conjecture. So let's think about the following moduli space. It's going to be tuples. It's going to be a, let me just put them down here, En and theta, where, what are these things? So X is a smooth projective variety. All these E's are smooth divisors on X. So it's smooth divisor. And then when I add them up, if I take E, which I want to be just the sum of the EI, that should be anti-canonical. So really I have an anti-canonical divisor broken into a bunch of components, and I want E to be simple normal crossings. So the union of all these guys is simple normal crossings. And then theta is an ample divisor. It's effective. It's not anti-canonical. It's just some ample divisor, effective ample divisor. And then finally, I said that E is SNC, but I want it to be as singular as it can be, being SNC. So I want E to have a zero stratum. If you don't know what that is, please ask me, and then I'll just tell you. It's an easy thing. But I assume most of you know it's a zero stratum, meaning there's a point where as many components pass through that point as you could have and still be simple normal crossings. So E has a zero stratum, but the condition I want is, but theta does not pass through, does not contain any zero stratum of E. Okay, so I'm looking at the set of these things, the moduli space of these. So again, I've got a smooth projective variety. I've got an anti-canonical divisor, which is SNC, and I have an effective ample divisor. And then I have this condition, degenerate condition. I say that E has a zero stratum. So it's got a maximal, a point where it's as singular as it could possibly be and still be SNC. And then theta doesn't pass through that zero stratum. Now, that last condition, that theta doesn't pass through the zero stratum, I hope you see that that's just equivalent to saying that this is just equivalent to that Kx plus E plus a little bit of theta is log canonical. That's all what it means, that theta doesn't pass through the zero stratum. So, and notice that this thing is trivial, Kx plus E is trivial, so this thing is linearly equivalent to theta, so this thing is an ample divisor. So what does that mean? This condition just means that this moduli space, let's call this moduli space Q, that these are stable pairs. So let me go to the next page. So if I look at X together with E plus a little bit of theta, this is a stable pair. So that means this moduli space lives in the moduli space of stable pairs. Now, if you don't know what the moduli space of stable pairs is, who cares? Because I'm going to talk about something totally different in the talk anyway, but this is just going to be an application. So this Q, this moduli space, it's a subset of stable pairs, and our conjecture is that there exists a complete toric variety, let's call it TV, and a finite map. Important thing, it's finite, and a finite map of Q, of this toric variety to the moduli space SP with image the closure of Q. Okay, so maybe informally, this is not correct, but how could you think of what I'm saying? You could say informally, I'm saying, this is not precise, but roughly speaking, I'm saying that Q, you can think Q is roughly, has a finite cover by a torus. I'm not exactly saying that because Q won't be exactly the interior of this toric variety, but it's almost this. I hope this is a surprising conjecture. For example, I'm saying this moduli space, the space of, what could this be? This is like, X is like a Fano variety, and this is some anti-canonical divisor in X. That's what I'm looking at. And then I'm looking at also a member of some completely different linear system. And I'm saying that the moduli of this is roughly a torus. you know, why should it even be why should it even be unirational? But I think it's actually on the nose a toric variety up to this finite cover. Okay, so let me explain.
I'm surprised, okay? And I also
Good.
don't believe it, but that's okay. That's cool.
Okay, well, let me give the proof.
You're still my
Okay,
friend.
it's not quite the proof, but let me explain what I'll explain in the talk is how I think you could prove this. And then, okay, so we go away from all this stuff and we just have a little bit of Berkovich geometry. So a little bit of Berkovich. So I have to have a field K which carries a non-Archimedean real valuation. So that's some function from the field, well, field minus 0 to the real numbers. What examples? Well, you could take, you know, take a discrete valuation field, take a discrete valuation. Discrete valuation, you could just take take the quotient field of a DVR, or you can actually just take which is going to be the most important example for us, take the trivial valuation. You just take identically 0. So just every field has the trivial valuation. That's perfectly fine. Now take X to be a scheme over K. And now there's a really cool notion, I believe, due to Berkovich, which is the analytification of X. So what is it? I'll give you the definition just to show how simple it is. It's just sets of pairs X and W, where X is a scheme point of, that's just a scheme point of our scheme. And what's W? Well, W is a valuation on the residue field, Kx, which notice contains K, which extends our valuation, extends V on K. Okay, so you just take all you do is you just add for every point, you add a valuation to the residue field. That's this Berkovich analytification. Now this is naturally a topological. Go ahead.
I think valuation in R or something like that.
Yeah. Oh, sorry. Real valuation. W is a real valuation. Yeah, on this thing. These are real valued valuations. Yes. This is naturally a topological space. I won't say the topology, but in 5 seconds you could guess what it is. But it's much more. It actually has a sheaf of analytic functions on it. Sheaf of analytic functions. It's an example of what's called a K-analytic space. Now, don't get scared by that. You don't need to know much about K-analytic spaces. In fact, as Tony will tell you, hopefully when I'm not in the room, I barely know anything about them. The only thing I really know is that if I go from K schemes to K-analytic spaces by analytification, this is a functor. And if you took only projective schemes, if you only looked at projective things and you only looked at maps between them, this is fully faithful. So, you know, there's just
Sean, maybe you want to write a K varieties.
I'm just going to leave what I got, and moreover, you know, there's what I'm saying. There's a Gaga principle here. So really, psychologically, and really for me, practically, it's just like if you have a variety or a scheme over C, there's a corresponding complex, you know, holomorphic analytic space. But that doesn't bother you. I mean, you deal with that thing exactly like a variety, you know, even though it's got holomorphic functions on it. And in particular, the important thing is, you know, maps between the holomorphic maps between projective. You don't get any when you take a variety, projective variety, you think of it as a complex analytic space, and you look at holomorphic maps between them, you don't get any new maps. They're all just the old maps. Exactly the same thing is true here. Okay, so what are some examples? So let's just, I want to tell you a little bit so you get a little bit of a feel for the analytification. Well, note, why should you like the verification? Note that the points of the algebraic closure, that's what K bar means, these live canonically in the analytic space, in the analytification. For example, suppose I take a point which is a rational point. Well, then K of X is just K. So there's nothing to do. So they're just in there. So W is just the original V. So they just live in there. And a really cool thing is that this, except in the case of a trivial valuation, this is dense. So now let me remark, what's this thing? This thing is, you know, like if you ever study manifold QP analysis over QP, this is a totally disconnected space. It's just, you know, it has topology like the topology of QP. It's just a ridiculous topological space. This thing The analytification, on the other hand, is a beautiful topological space. It's locally compact Hausdorff space, and it's connected whenever X is connected as a in the Zariski topology, locally compact Hausdorff space. So it's just amazing. You take this totally disconnected thing and you fill it in, you fill in all the holes in a canonical way. Let me give you an example. The only example that I really
think your schemes are separated.
Yeah, let's take X to be P1, which in this talk, a lot of times I'm going to call C bar. Stupidly, I'm going to call it C bar. But anyway, you've got P1. What's the analytification of this? Let's give you a little feel for it. Well, it's what's called, it's a tree. It's a big tree, but it's what's called an R tree, which I couldn't give you the precise definition, but it's a tree except if you have a vertex, the valence at the vertex, the number of edges coming in can be infinite, is infinite. So it's kind of hard to draw, but for example, I can still kind of give you a feel for it. The K points, let's take K to be K bar, so we don't have to talk about K bar. If I take the K points, these give leaves of this tree, of the tree. So, okay, so the tree has got these, if you've ever seen the building for PGL2 over a DVR, this is very close to that. These are the points XK. They're leaves of the tree. And now let's pick, I can't draw the tree because the valence is so big, but let's pick a bunch of rational points, P1 up to PM in X, which is my C bar. And I'm always going to call C the complement, by the way. C bar minus these points, P1 to PM. Okay, so I have a bunch of points on the leaves of this tree. And I'm in a tree now. I'll do it with 4 here. Then, because it's a tree, I can talk about the convex hull of these points, just the smallest subtree that contains them. And what you get is a really nice thing. This thing lives, this convex hull, it lives in M0, there were M points, M0, M trop, which is, what is that space? That's the space of, that's the, the tropical M0 N trop, this is the space of metrized trees. I hope some of you studied this M0 N trop, just these graphs with metrics on them. It's a real nice thing. So, and then it's an easy thing. And that's what this is. You get this metrized tree. And then what else do you have? And then there exists a canonical retraction. This is just true anytime you have a subtree of a tree. There's a retraction of the whole thing onto this little subtree. So, for example, how can you kind of visualize this? You might take 0 and infinity inside of this P1. Then this convex hull is just a straight line, is just the interval 0 infinity, and we have this retraction of the analytification onto 0 infinity, and this map inside of X analytic we have the rational points. This map is just the norm. Turn the valuation into the norm by doing something. I hope I have it right. I think you take the exponentiate minus the valuation. So norm or valuation is the same thing. So this is basically the valuation map on the points. And that's what this retraction is. So what does it mean? So the whole thing, we have all these, here's all the leaves. This is, XK out here. And then for each point, well, it's hard to draw this thing because it's an infinite tree, but the whole thing, kind of the whole big tree retracts back onto 0 infinity here. But let's notice, for example, let's say I stop, say at S. So I've got this retraction, I'm calling it R. I could take X and I can write X as the union of 0S, union, the inverse image of S infinity. And this is what's called a closed analytic disk. And it is just a disk. This map is just norm. So, on these points, these are the set of X where the norm of X is less than or equal to S. There's no question that that's a disk. It's a closed disk. These disks are perfectly nice K-analytic spaces. These are nice K-analytic spaces. So in this world, that's what I like about what first attracted me to this world. The disk, the closed disk is a nice algebraic object. That's an advantage it has over ordinary algebraic geometries. You have the disk. Okay, we've got this guy here. And also, let me mention, I should have said it, that we had this convex hull. Remember, we took the convex hull of those points. This thing, except if you throw away the points themselves, this lives inside of C analytification. Remember, C was take C, the P1 and throw away minus the points. So it's punctured P1. This thing lives in it, and it's actually a canonical thing, canonically associated. It's what's called the intrinsic skeleton of this curve C. So this is just this. So that's a very cool thing about this world. You take a punctured, punctured rational curve, or a punctured curve of any genus. Inside of it, there is just a God-given tree living inside of it. I wanted to stress what's really great about this world, and this is why I got attracted to it, is if you take a punctured rational curve, in this world, it living canonically inside of it is a graph, the sort of tropicalization of the curve. Just comes with it. It's this canonical skeleton inside. Okay, let's give a, let me go further. So tell you more about the analytification to make you happy with it. So let's take V here to be some smooth variety. Suppose I've got it inside of X. This is some SNC with SNC boundary. It doesn't have to be compact at the moment, but I'll always write the boundary as D. So that's X minus V. So that's the complement, and I want that to be SNC. So this is an open set. This is a risky open set, V inside of X. And let's say in this case, just because it's easier to describe it, for what I'm going to say now, let's say K is trivially valued. Trivial valuation. And then we do just what Bernd was doing. Let's take sigma, which is really sigma XD. That's just the abstract dual fan, the dual fan to D, or maybe it's to XD. Just like Bernd said, it has, how does it work? It's got rays that correspond, the rays correspond to the irreducible components, DI and D. And it's a simplicial fan. So there'll be a k-dimensional cone. It'll be simplicial. Simplicial. One of those for each of the codimension k strata of D. And then the thing is that this abstract fan, the underlying topological space or piecewise linear space, the underlying space of it lives canonically inside the analytification of V. So this is cool. So the kind of the base of the SYZ vibration, the analog of that, it lives inside of our space. How does it live in there? Why is it there? I'll give you some idea about it. Well, for example, let's take one of the rays. Let's take DI. That's one of the irreducible components of D. Remember, D is X minus V. I want to say that there's a natural corresponding point inside the analytification. Well, analytification were these points, pairs. So what's the pair? Well, what's the scheme point? You take the generic point. The generic point of the scheme, so that the residue field is just the quotient field. And what valuation do you take? Well, I have a divisor, so I take the corresponding discrete valuation. I hope you know what I mean. If you don't, please ask. It's just the divisor, the valuation you get on the field of fractions by the divisor, or orders of 0 and pole along there. So this point just lives in, by definition, this lives in the analytification. So, and then moreover, because K is trivially valued, so K is a trivial valuation. In this case, there's a scaling on the analytification. Just leave the scheme point alone and just multiply the valuation by this positive number. So just multiply the valuation by the number. And so, okay, so I can draw a little picture now. So here I had this, let's say here's the dual fan, maybe dual to two-dimensional picture. This is my picture of my XD, and this is the dual fan, sigma over here. We just said you got this point, these correspond to the Ds. There should be as many rays as there are things there as boundary divisors. Over here, I've got my little DI, when I scale it, I get this. When I scale this, I get this. I'm not going to show you how this sits in there, but it'd be easy to describe. So I get this. So I get this whole fan living inside the analytification. I have the subset of the fan. It's divided into chambers. For example, let's say that V is log Calabi-Yau, and let's say that omega is the volume form. And in this case, let's talk about what Bernd was calling the good divisors. Remember, I have this partial compactification here, and I have the boundary D. Inside of it, let's take the essential boundary. These are all the DI where where omega has a pole. And then in this case, if I take the fan corresponding to V and these essential divisors, that lives in V analytic, and this is canonical. This is what's called the skeleton of V. It does not depend on the compactification. This is a completely God C star. So this is, again, there's nothing fancy here, where this is just an algebraic torus, C star to the M. In this case, the skeleton, the canonical skeleton of V is just exactly the same as the canonical skeleton of the torus. And that's just the place where you draw the fan in toric geometry. That's just MR. That's just the real vector space given by M. So M tensor to R. Also, let me remark that, you know, there's integer points in the analytification. So inside of here, there's integer points. What are those? This comes with natural integer points. Well, what are these? These are the valuations. The valuations. Well, or they're all of the type, you know, the generic point followed by some valuation on Q of V, and these are the ones that you get by taking divisors. These are the ones given by a divisor in some model. In some model, a divisor in some model where omega has a pole. That's what the primitive things are, and then you can multiply in this world. You can multiply, or then multiply by positive integer. So it's a positive multiple of the valuation given by a divisor in some compactification of V where omega has a pole. That's the integer points of the skeleton. And this is just, if there was a torus sitting inside, this would just be M, the place where you draw fans in toric geometry. Okay, so where are we at here? I talked about these skeletons. So this is, to me, what's cool about Berkovich geometry is it's got two things inside of it. It's got, inside the analytification, you've got sort of algebraic geometry. That's just ordinary, it's algebraic geometry. The old scheme lives in there, at least the K points of it. And there's also these piecewise linear things. Piecewise linear things, like in the case, let's get rid of X and let's go back to V, which was the Calabi-Yau. It has this canonical skeleton. That's a thing which is, let's think of it as it's almost an Rn. It's a Q homology Rn by a theorem of Janos. But for example, it's when V contains a torus, it just is Rn on the nose. So inside of here, you have algebraic geometry and then some version of tropical geometry just built in. It's pretty cool. So let me give you an example I think that I really love about this. So let's, again, V is now, oh, just a remark that this canonical skeleton, the dimension of the skeleton, it's always, you know, as a real thing, it's a piecewise linear thing. Its real dimension is always less than or equal to just the dimension of the variety. And if we have equality, we say V has max boundary if there's equality. And that's the case I'll always be talking about, max boundary. So let's say we're in that situation, and I want to show you a cool thing. So let's pick, I'm going to do it on the next page, just because maybe you'll be able to follow it better. Let's pick P1, PM in the tropical set. So these are some, and let's write them as DI, DI. So, you know, because they're multiples of an actual divisorial valuation. So DI is the divisorial valuation. And then let's pick a compactification, compactification now with SNC boundary, which I always call D. And I want all of these DIs to be part of D. So you can always do this, of course. Just take a compactification and blow up enough so that you get all these divisors in it. Let's look at this picture. And now I'm going to look at a natural moduli space, which is, I'm going to pick also an alpha in the Mori cone of X. So pick a curve class on X. And then let's look at the moduli space. I'll call it M of U, although it's really M of, depends on U, all these divisors, and alpha. And what it's going to be is, it's going to be pairs of a rational curve, that's just P1, but I call it C bar, with a bunch of points in it, P1 up to PM, and one more point that I'll call X. So this is just an element of M0, M plus 1. Ordinary algebraic geometry, you know, M plus 1 points on P1. That's all we're doing. And then I have a function, of course, an algebraic function, taking C bar, my P1, into X with the kind of boundary contact that Bernd was talking about, where the condition is that the inverse image of D, the pullback of D, the boundary, should be, it only touches the boundary at the points P1 to PM with the given multiplicities, DI, PI, where these DIs were the multiplicities of these divisors. Notice I'm using the same letters for these P's and these P's. That's because these are the places where this guy touches those things. These are divisors, or multiples of divisors. These are just points on a curve. Okay, so let me draw the picture here. What are we saying? You know, here's what XD looks like. That's XD. I've got some boundary divisors, maybe D1, D2, maybe D3, and I'm studying rational curves that only touch the boundary at, this thing goes away every once in a while. They only touch the boundary only at those boundary divisors, and where it touches with the multiplicity that I prescribed at the beginning, these DIs. So I've got that, and there's one more point on here, X. Notice by construction, f of X is in U. So this moduli space, which I'm calling M, comes with a natural map. So M comes with a map to M0 MM cross U. What's the map? I hope it's clear to everybody. This was a pair of, you know, C with a bunch of points on it and a function from C bar to X. What do? You just map this to the domain. You map it to you map it to C bar together with its points. That lives in here, and then just where the last point went, f of X. This is crucial, so I hope you see what we're talking about. We're just looking at a space of pairs of a curve with a bunch of points on it, and a map of that curve into X. And I map, so what's this map? I just remember the domain, which is a P1 with a bunch of points. That means, you know, this is M0M, everybody's favorite thing. And this is U, my variety, and then I go where the last point goes. Okay, and now we take the analytification. The analytification has exactly the same meaning. You just put analytification everywhere. Goes to M0M analytification cross U analytification. What would it be? What's M0M analytification? It's the space of analytic P1s with M points on it. It has no information that isn't already in M0M. It's just the analytification of it. What's this? It'll be a space of analytic curves. So these are analytic curves with maps. Curves now. They're just P1s, again mapping into X. Just put analytification everywhere. Just behaves exactly the same way. But why is this better? Let me erase this last bit so it doesn't get in the way of the picture. Oh, if I'm able to do that. Yeah, let's get rid of that part. Why do I like this better? Because now there are natural skeleta in this picture. So inside of this guy has a natural skeleton. Remember, how do you get a skeleton? You just compactify the thing and take the dual complex of the boundary. So you would know how to compactify M0n. What would you take? M0n bar. You were already compactifying to X. So inside of this thing has a canonical skeleton. It's actually intrinsic to the variety, and it's equal to just what is it equal to? It's M0n trop, that's the space of metrized graphs, crossed with the skeleton of U. That's the version of the thing that Bernd was calling B. You know, that's the tropicalization of U. But here it just lives in U. So we have this map. We have this natural skeleton living inside the target, which is a thing we completely like. Let's just be stupid and study the inverse image. So I call it ISK for inverse image of the skeleton. So just phi inverse of the skeleton that lives in here. So what is this? Well, it's some subset of maps of curves into X, analytic curves into X. But they have a really cool property that Tony and I observed. So the observation, which is really easy to show, is that if I take F, let's take F inside of this ISK. So, so what does it give me? F gives me a map of the analytification of C. C, remember, was the complement of the points. I've got a P1 with a bunch of points. This is the punctured curve. That's mapping by F into U. Inside of U, I have, the tropicalization. That's the skeleton of U. It looks like sort of an R2 if it's two-dimensional. That's sitting in there. Inside of here, I have this canonical graph that I drew. That's the skeleton of C. What would you wish happens? What could you hope for? You could hope that this guy lands in this guy, and it does. So the observation is if F is in here, that when I map then under the map that I'm already given from C into U analytification, the tropicalization of C, this graph that lives in C, just happens to map into the graph, this fan, or the support of this fan, this linear thing that lives in the analytification. So this we'll call, maybe we call this, we call that the spine of F. Or we could have called it tropicalization. So in this world, curves with this property, analytic curves with this property we call skeletal. Skeletal curve. That means, you know, analytic maps which have this magic property that their graph just lands inside of the tropicalization of U. We call these guys skeletal curves. They come with a tropicalization. But it's none of this nasty stuff, you know, with logs or anything. This tropicalization is just the restriction of the map. So it's just right there to start with. Something even better you can do, using this, we can count tropical curves. We have a completely naive way of counting tropical curves. How should we do it? So back to the picture. Well, first of all, so let's take a tropical curve. What do I mean? Let's take some gamma in M0, M plus 1 trop. So, you know, it's one of these. It's one of these trees with marked points. Plus, it has M plus 1. It's got this one extra point. So P1, P2, P3, P4. And suppose I have a continuous function, just a function. I have some function, let's call it S, from gamma into Sk of U. This is this thing which is, sorry, Sk of U. This is this thing which is like MR. It's like Rn. That's the tropicalization of U. Suppose I give you just a continuous map, no balancing condition, nothing. Don't even really need continuous. Just give me a function from gamma into SKU. And I want to count it. I want to count it. How do I do it? Well, notice that if I take the pair, let's go back to that diagram that I drew. What was that diagram? It had ISK, that mapped to the skeleton, and the skeleton lived inside of, over here we had M0, M plus 1, cross U, everything analytified. And here we had the space of analytic maps. Well, okay, let's look at the pair, gamma, together with the image of the last point, S of X. That lives in here. The skeleton here, remember, was the product. It was M0, M plus 1 tropicalization cross the skeleton of U. So there's a point in here. I've got this map phi. I've got this map phi here. Oh, shoot, I should have mentioned, let me mention something at the moment here. Same picture, but let me make a remark. That easy deformation theory shows this, that if I look at the map from M of U to M0, M plus 1 cross U, just taking an analytic map, take its domain, and take the image of the last point. If I call this thing phi, it's generically finite étale. What do I mean by that? I mean, after you throw away a Zariski closed set from this and restrict, the map is finite and étale. That's just Mori style counts of rational curves. So that's an easy thing. The skeletons are highly generic. They miss any Zariski closed set. And so when I go to the tropical picture, when I go to the analytification here, and inside of here I have the skeleton, and here I have ISK. This is phi. That phi is finite étale around SK. There'll be some neighborhood of the skeleton where this map is a finite cover. That means the fibers here are really just smooth, zero-dimensional. So the fibers are just smooth and zero-dimensional, or zero-dimensional and smooth. They're just a discrete set. Once you extend the base field, they might, they're just a set. They're just a set, a discrete set. So I can count them naively. So now, how do I count tropical curves? So now, how do I count this tropical map, which was just a map of a graph into SKU, just a set theoretic map of a graph into SKU? What I do is I take phi inverse of this point, the domain, together with the image of the last point, comma, and S of X. Where does it live? Well, it lives in ISK. These are all skeletal. So this inverse image, and this is a finite set. So this is just some discrete set after base extension. That's a discrete set of skeletal curves. So these are all just analytic curves, and they all come with a tropicalization, and I just take the subset of these guys. These are all maps of C bar into analytified into U. I take the subset of them whose tropicalization, such that S of F is equal to S. So in other words, I look at those curves whose domain, when I look inside the domain, there's this metrized graph. That metrized graph should be gamma, and then the map that their tropicalization has to be the given map. It's a finite set, so I just take its cardinality, or take its length if I was still, if I hadn't base extended. So that's it. That's the count. Note, I mean, there's no balancing conditions here. There's no multiplicities. That's how you can count tropical curves in this world. Okay, so I think that's pretty cool. So the point of this was really just to get you a little bit comfortable with the analytification, or with some Berkovich geometry. Now let's connect this with mirror symmetry. So now we're going to start. Now we're going to take V just as before, but now let's say it's going to be affine. Log Calabi-Yau, affine log Calabi-Yau, maximal boundary. And let's fix some SNC compactification.
Hey, Sean, can I ask a question?
Yeah, sure, please.
You just mentioned V affine. Didn't you need affine before to have that finite et al. Generically?
Not the finite. I didn't need it for the finite, but I needed it for but not for the et al. But if I wanted it to be,
finite. Sure. Okay.
If I wanted it to be finite after throwing away a closed set, yes.
Yeah. Okay.
Yes, I needed the affine for that. Thanks. So here I have V and X. This is a SNC compactification. And let's let R be, which is really Rx, be the monoid ring of the Mori cone. So, what does that mean? Just means direct sum over curve classes of Z times the formal variable, X to the alpha. And you multiply in the obvious way, just by adding curve classes. So that's the monoid ring of the Mori cone. And let's let A be the free, it's going to be the free R module with basis the tropical set, SKU Z. And so we're just going to write it as formally as, we write it formally as just the direct sum over P in the tropical set of R, our coefficients, and then just a basis vector that we're going to call theta P. And then if you expand out what R is, you get the direct sum over these things, these boundary divisors P, and then the curve classes alpha of just now integers times theta P X to the alpha. So it's just, this is just a free abelian group at the moment, which I partially erased. So this is Z theta P X to the alpha. The conjecture, main conjecture of Gross, Hacking, Keel, and Siebert is that this thing is naturally a ring. Naturally a ring, in our module, in our algebra. It's naturally a ring, and it's not just a ring. And then if you take spec of it, if you take spec of A, notice that maps down to spec of R, which I should have mentioned, that's the toric variety given by the Neff cone of X, just by definition. Inside of here, we have a torus given by the Picard group of X. If we restrict, let's call this thing maybe U. No, I called my thing U, I think. Let's call it V. I can't remember what I called my oh, that was called V. Let's call this U. I look at the family that I get. I get a family out of this, and the conjecture is that this is a family of affine log Calabi-Yaus, and it should be homological mirror symmetry dual, to our original U, and in fact the ring A should be the symplectic homology of U. This is a conjecture. So what do we have to do? So the problem is the first problem is to put a multiplication on A. But notice, if we go back to the picture, it's this free module. What does it mean to give a multiplication rule? It just means giving structure constants. That's equivalent to structure constants. That just means you take theta P1, you want to know how to multiply a bunch of these guys, a bunch of the basis elements. You're supposed to get some answer, which will be a sum over these kind of tropical points, the boundary divisors and curve classes of some number that depends on those guys, you know, x to the alpha theta p. So you have to get these numbers. And in our construction, these are going to be elements of just positive integers, non-negative integers. So how do we get them? How do we get them? I want some numbers. So I'm given this data and I want to produce a number. And I want to show you that in the Berkovich world, there's just a kind of a really simple thing you can do. So I'm going to tell you, how do you get these numbers? Bernd told you one way of getting these numbers. That talk he was doing was giving these numbers. Here's how I'm going to get these numbers. So what are we given? We're given P1, PM, and also P. These are all, I'll remind you what these are, and then I have alpha. That's just a curve class. It's a curve class. So what's the picture here? Well, let me show you again. Here's our x. I'm showing you the boundary of x. This is our xd. What are these PIs? Well, they correspond, I'm going to think of the first bunch of them as giving me boundary divisors with multiplicities. You know, they're just as before. I'm writing PI exactly as I did before, as DI, DI. So I've got these, you know, some D, so D1, D2, D3. That's what they tell me. What does P give me? I think of P in a different way. P, where does P live? P lives in the skeleton of U. Well, that lives in U in this world. So let's think of this picture as the picture of the analytification, and P is just a point in there. And here's what I want to do. I want to count maps of a disk together with some points, P1 up to PM, very much like, almost exactly like what I just had. P1 up to PM, and one more point X. I want these to map into the analytification with the same boundary contact as before, so that F inverse, F upper star of D should just be these points with the given multiplicities, DI, PI. And I want F of X to be the point P. So I just count disks that map in with those contacts, and I want the mark point to go to here. Now, I can't count this because these are disks. That's an infinite dimensional space. Disks are no good for that. I need P1s. But I add a boundary condition. So we add a little boundary condition. Boundary condition, you know, on our map. We ask that it extend to a map to, you know, C bar, which is going to be this D union, just same picture I had before, two disks. D union, what I'll call D infinity. D infinity is going to have one more point in it, one more K point in it. Well, I was going to call it infinity. This D contains, this one had the points P1 up to PM together with our X. And what do I ask? I want to extend F to a map now of C bar into X, just like before. Now the upper star of D, the pullback of D, is the PI, sorry, DI, PI, just like before, and the one extra point of contact, so with some multiplicity. So what's the picture? Maybe draw the picture here. Our original thing we counted were disks that had some contact with the boundary at the points, at the given points. Here's my disk D. It touched at the given points. These were sort of the PI, and its marked point went through P. And now we extend it. Here's D infinity. It has one more point of contact. Oh no, sorry, I don't call it X. I was already calling my point X, I think. This is some new. This guy had P1 up to X. This has one more point of contact in it. This C bar had one more point. It had all the points P1 up to PM. The point, I think I called it X, and then one more point. Let's call it Z. So sorry, the extra contact. What's that?
You called
Let's go back and see what I called it. Yeah, that's right. So go ahead. What's your question?
I just said you called it infinity.
Oh, infinity. Oh, that was a good name for it. Yeah, I should have called it infinity. I will call it infinity. So that's infinity there. It has an extra point. Okay, so what's the picture here? Okay, so we have this, and now I have to put one more condition. But everyone getting it? I wanted to count disks that had contact, but I can't count disks. That's infinite dimensional. So instead, I count P1s, which have this disk plus a disk glued on. They're allowed to touch one more time someplace. I'm not telling you where, and I don't tell you where. I just ask this. But the condition that's actually forced by a different condition, which is this. The last condition, the important condition is now I need to assume that U contains an open torus, contains an open TM inside of U. And then what I ask is, I ask that this map takes D infinity star into the torus. So what do I mean by star? That just means, star always means throw away the mark point. So that's just D infinity. It's just a punctured disk. That's just D infinity, take away infinity. So basically back in this picture, all of this except for that, this part here, the end goes into the torus. Okay. Now, how do I count such a thing? How could I possibly count this? How to count? Well, that's no problem at all by what I just said, because this lives, what are we looking at here? This lives, this map of C bar into X now, that's my extended thing. This was D union D, this D infinity. This lives in M0 from before. So these are just, there I can just count. I just take the fiber over yeah, I mean this is exactly the thing I was just counting. I'm giving you, I mean, these are a subset of what I was calling phi inverse of some point, which I can take if I like to be living in the skeleton. If I fix the correct, anyway, sorry, these are, in any case, they're so just a fiber of this phi. What was this phi thing? Now we'd have our mu would be mapping into M0. How many points have we got? M plus 2 now cross U. And that was my phi. And the things I'm counting, I fix, I just fix a domain in here and a point in U. I've done that. This is my P. Here I fix, I can pick one, pick one, 1 point, and just take the fiber. I can take that point if I like inside the skeleton. And then I take, here we had that ISK. So yeah, so I have a subset. The things I'm counting, things we count, are a subset of this discrete fiber. I make a choice here. I have to take a, what I'm really doing is when I do this, I'm fixing which analytic curve I take. I'm taking analytic curves inside the skeleton here. Drop. I'm saying the domain should be one of these curves. I'm fixing it. So there, there's things to prove here. But the theorem of me and Tony from last year is it works. So first of all, everything is independent of all the choices I made. For example, it doesn't matter. It's independent of which torus I picked. And these, the way when I make this count, I have to pick the fiber over some point. It's I have to pick which I just erased it. I didn't mean to do that. M0, M plus 2. I have to pick the point in here to take the fiber. It doesn't matter where I pick the point. So same kind of things you always do with counts. I have some choices. I have to prove that the thing is independent, but it works, which means that we get a family of log Calabi-Yau's, and we show it agrees with the families that already existed at that time, which were in dimension 2. This paper of myself, GHK, that was dimension 2, and GHKK, that was with Kontsevich, that was for clusters. So, sort of showing we're getting the right thing. We use this definition and we prove that it works, that we recovered the previous cases. Now, I had to assume, so I wonder if people got this. I wanted to give you the feeling that this was simple. So what did I do here again? I wanted to count. What did I count? You know, what was I given? I was given a bunch of boundary divisors with multiplicities. And I was given, and then the smart thing is to think of the last guy, the last P, not as a boundary divisor, but just a point of the analytification. And then I just wanted to count disks that touch. You know, I just count disks that touch at the boundary. They pass through this guy. That guy's on their, that point's actually on their boundary. Goes like this. That was the things we wanted to count. How do we count them? We just counted them by counting P1s by adding on a disk. And the count of the P1s, that was completely naive. There's no, it was just set theoretic. There was no virtual fundamental class, anything. It's just cardinality of a finite set. Now, I needed, what did I needed here? This, I wanted to say that I wanted the end of this disk to land in the torus, or the punctured part, to land in the torus. For that, I needed a torus. The count does not depend on which torus you pick, but I needed the torus. What to do in general? So, Bob, in general, this is just speculation, but the idea is, in general, if I don't have a torus, or even if I do, I take X, my target, and I just add on to it a torus. I can glue it on. In the Berkovich world, there's lots of places inside the analytification that look just like a standard neighborhood in the torus. So you can glue this on. This is an easy, natural Berkovich construction. And now I'll just count maps like this and do the same thing. And now just count curves in this extended thing. It'll actually be a slight a toric variety with one boundary divisor that I glue on. I count curves in here with the same condition. And then I ask, again, that D infinity star map into the torus. So we haven't done this, but we're thinking about it. I mean, we've been thinking about it. It looks reasonable to me. It looks good. I think it's going to work. Why is it harder? The main reason it's why didn't we do it before is that this is a purely Berkovich thing. Berkovich. This is not the analytification. This is a K-analytic space, a nice K-analytic space. It's not the analytification of a variety. Before, because our target was the analytification of a variety, we didn't need to prove any theorems about deformation theory of rational curves or anything. It all just came for free from algebraic geometry. So here we need to do some foundational stuff on counting, but Tony's done most of that stuff already. I forget his coworker, Mauro, I think his guy's name is, Mauro. They've done pretty much all that. So I think it's going to work out, but we still have work to do. Okay, Matt, how much time, Mark?
Sorry, it takes me a little bit of time to unmute. 5 minutes, say?
Oh, okay, then I'm going to take possibly slightly more because I want to connect with the original conjecture. Connect with the conjecture. Why is this a proof? How come we think we can prove the conjecture now? Well, let's go back to the conjecture. So if you totally forgot everything, let's talk about the Fano case of the conjecture. So that means I want to study the moduli of a Fano. E was this anti-canonical divisor. This is SNC anti-canonical. And the theta, the Fano case, I'm going to take theta to itself be anti-canonical. I could have, in my conjecture, I could take any ample line bundle. But here, let's take the case where theta is in minus kx. So how do we prove this? And we have I also have it would just take a little bit longer. I have a scheme for doing the general case also, but it's a little simpler to explain in the Fano case. So how do we do it? So let's start with a Fano y. It's going to be mirror to x, and D anti-canonical. So this is again Fano. D is in minus ky, and let's let U be the complement. Y minus D. That's going to be affine now, and I want it to have max boundary. It should be the mirror. I mean, we just start with this and run a machine, but to get the x that we want, we should be taking the mirror to that x. Let's start with this, and then take k over y. That's the canonical bundle. Notice because I've got D is anti-canonical, that gives you a function on k. So this k comes from D, comes with a map to A1. And inside of A1, I have GM, and the inverse image of that, I'll call V, and it's actually isomorphic to U cross GM. So this is again a log Calabi-Yau. So this V this guy's, this V, he's log Calabi-Yau with maximal boundary. And what I do is I just run the machine, for V living in K. K is not projective, it's not compact, but notice K has a map. This is the canonical bundle of a Fano. It's got a map to K bar, which just sends Y to a point. So this is just the affine cone over Y. So this is an affine variety. This is projective. So it's just as good. It's projective over affine. So I just run the machine for this. And I get this ring A. Under this map, remember K had this map to A1, given by D. The equation of D gives me a map to A1. That gives me on V a map to GM. Because I have this function here, maybe I'll call it little d, D, just easy with our definitions of the counts, this D makes A into a graded ring. Makes it into a graded ring, gives it a grading. Any function would give it a filtration. Because this function is invertible, I get this to be a graded ring. So I take X to be proj of A. It comes with an O1. And how does that work? Well, it's the boundary. If I take the boundary of K and V, so take K minus V, let's call that DK. That's the central fiber of this map. Central fiber of this map to A1. What it looks like, let me show you in dimension 2. What this D looks like, it's got one component is just Y, the zero scheme, or the zero section inside the canonical bundle. That's one component of this DK. And then it's also got the K, the line bundle K, restricted to the old D. So maybe I can draw a picture over here. Here's a picture of YD. Or maybe I should draw it like this. That's my YD. But what's this DK? Well, it adds a flap. It adds a line bundle over each of these boundary divisors. So I get a thing that looks like this. Notice what its dual complex looks like. It looks like a polygon with one interior lattice point. So, and that's what's true here. So actually, if we look at this fan in this case of K with this DK, that's abstractly a cone over a polytope. This polygon, at least the underlying set, naturally lives in the skeleton of V. I mean, so does the whole thing here. It lives in here. It's like a reflexive polytope. It's like reflexive. It's not. I mean, there's no affine structure here. This is just a piecewise linear thing. Piecewise linear, but it looks like a polygon. It looks like It looks like it's reflexive in the sense that if we were doing a toric case, it would just be an honest reflexive polytope. It looks like a polytope with a unique interior lattice point, just like in the picture I just drew. And what is that lattice point? It actually corresponds to the divisor corresponding to Y. So that lives in the integer points of this Z. Okay, so I was telling you how do we do this thing. So what was X again? X was proj of A. H0 of O1, that has this theta function basis. Just by construction, it will have a basis given by the integer points of this polytope, just like in the toric case. And I want to give this guy a boundary. I take E inside of X, that's going to be the divisor, which is the zero locus of this special point, the interior point. And I'm going to take theta to be the zero locus of just the sum of all the basis elements, P and PZ of theta P. So now I just have a family, X, E, theta, living over the toric variety for the Neff cone of Y. Okay, and what do we conjecture? I don't have time to say all the things we can prove, is that the fibers are stable. X, E, theta. We know that I can say we actually know that X is Fano. We know that E is anti-canonical. We know that KX plus E is log canonical. What we don't know in all cases is that theta, does theta, the question that we haven't proven in general is, does theta pass through a zero stratum? Does theta pass through a zero-dimensional log canonical center of the pair XE? That we don't know in general. But we have this family, and now let me just say, in my conjecture, what did I say? I said I was going to get you a complete toric variety, right? I don't have a complete toric variety. I have the toric variety for the Neff cone of Y, which is actually the same as the Neff cone of K over K bar. So again, I had K over here, or the canonical bundle, and it has this affine cone. But here's the complete fan I can take, is the Mori fan of K over K bar. That's complete because it's projective over affine. That's a complete fan in the Picard group of Y. And the claim is that our family extends canonically. Everything just extends essentially with no work over the toric variety for the Mori fan. Now, why should that be true? You know, how the hell can we extend it to this complete toric variety when I only had it over a little affine piece? Well, what does that really mean? Let me just tell you, a lot of you know this kind of thing. Here I have K going down to K bar. What is the Mori fan about? It's about flops of K. This is a flop. Here we have this open set V. It will be disjoint from the flop won't change V at all. So we've got V living in K. We've also got V living in K prime, and we could just as well run the machine here. Run the machine here. We'll get two different rings. Here we have the ring A, you know, coming from K from v, containing V, and over here we'd have the ring A coming from this flop. We want to know that these rings are basically the same. Well, once we invert some coefficients, we want to know that these are equal. Okay, well, why should they be equal? Well, they have the same basis. They have the same basis. It's the skeleton of V. And what else? It has the same multiplication rule. That's the hard thing. Why are the multiplication rules compatible? Well, the reason is, what are we doing? We're counting disks in V. V isn't changing under this procedure. So our definition just comes with it by a birational invariance completely from the beginning. So that's why with no work, we get this thing on here. So I get this family of triples, just like in the conjecture, over the toric variety now for the Mori fan. It's complete. This is a complete family. I hope you all can still hear me. Shit, I wonder if you can. Mark, make some noise if you still hear me.
Yeah, can hear you.
Okay, good, because I lost my other computer, but okay, we're still here. So we assume that the fibers are stable. That gives me a map to the moduli of stable pairs. But bad news, it's not usually finite. I could explain a little bit why is it not finite? It's basically because what can happen is when we have a flop, here we have K over K bar, here we have this K prime over K bar, and this has this map to A1. There are flops which don't change the dual complex. If I have a flop which doesn't change the dual complex of the boundary, doesn't change sort of sigma of D, then those will lead to some fibers. Those lead to some positive dimensional fibers. So this is not quite the right thing. But we did a cool thing. But we found a canonical coarsening of this thing, which I won't have time to discuss, which we call the secondary fan. Because it really is, it has to do with changes in the dual complex. This is a coarsening of sec, and again, just formal properties of our ring imply that the family comes from here. So in terms of the map, here we had Mori fan. I coarsened the fan, but had the same support. I've got the secondary fan, and the family, which is coming from moduli of stable pairs, comes from here. And this, we conjecture, is finite. I'll say a word about that. Our theorem is that it all works in dimension 2. Works in dimension 2. Why is this a cool thing? Let's think about, let me just say, finally tell you, why is this cool? To try to prove that this is finite. How could you possibly do this? What does it mean? You know, we've got this family, we've got this crazy ring A with this mirror algebra A, whose multiplication rule is given by counts of analytic disks. How could we possibly prove that this family is that the map to moduli space is quasi-finite. You have to show that the fibers are not isomorphic. But that's why it's nice to have a complete toric variety and have the right toric variety. Note, if I have a complete toric variety mapping to a scheme, so that's a scheme, that's a complete toric variety. Complete toric. It's finite if and only if no one stratum is contracted. Maps to a point. So you don't have to understand our family. Our family is defined over this huge complete toric variety. So X is complicated. It has to be. It's versal. It's the universal deformation of this Fano. It's complicated, but over 0 strata of the base, it's completely trivial. It's something like, it's like proj of a Stanley Reisner.